Oh, hey everybody, I'm here at my table, and today we're going to talk about RICE tables. RICE tables are ways we solve problems in chemical equilibrium. It stands for reaction, initial, change, and equilibrium. And so I think it'll be a good time seeing as we have our RICE table all set up. Does this picture look grainy? Okay, let's go to work. Well, greetings everyone, greetings, Mike here. Today we're going to talk about chemical equilibrium. It is chapter 13, not unlucky though if you don't make it that way by reading it, in the OpenStax textbook, and we're going to talk about reaction as an example. And I want you to notice something. Here's nitrogen monoxide reacting with oxygen to make nitrogen dioxide. What's the double arrow? The double arrow tells you this is an equilibrium situation. Another way to look at this is that the reaction is reversible. And so what happens is you're going to strike a balance, equilibrium, between products and reactants, where after a while there'll be some of everything present. And so what might happen here, let me try to show you what might happen, is the reaction will start and it'll be just like kinetics, and something will happen where what we got going on is like something like that, and then it'll go NO. This will be NO, by the way. And then we'll have a flat line. So we'll call that concentration of NO. And you see that it kind of just going to stop and not go to completion. Now you got to pay attention here. That change was what I tried to make about a change of about 0.6. It went from 1 mole per liter. This is concentration. This is, by the way, what we call reaction progress, or unless you're from Canada, you'd call it progress. So what happened is, as this reaction went along, the amount of NO decreased, but not to 0, but it went down 0.6. Now, because the change of O2 is 1/2 of that, and this was a change of 0.6, then O2's change would be less, and it would level out at like 0.7, see? And now the change in NO would be 0.6, so this would be the mirror image, and it would go up, and everything would like level out. So that would be concentration of NO2. So I'm going to draw a little dotted line here. This is the point, and I'm sorry, that should have been, that line should have been straight, where everything sort of stops changing, but it didn't stop changing. It just reached a point of equilibrium, and this is where all concentrations are constant. All right, so this is actually changing, but nothing is giving way in terms of concentration, because this rate of production of the products is equal to the production of the reactants, and now they're both going the same rate, kind of like when the price of eggs doesn't change because there's equal number of buyers and sellers, and then a shortage of eggs might happen and there'd be less, more buyers than sellers, and then that would change the price of eggs. But here we've got nothing changing because the rate of the forward reaction is equal to the rate of the backward reaction. And so what we tend to do is try to talk about that equilibrium so we can predict what will happen. A lot of important reactions are actually a case of equilibrium. Case in point, we're going to talk about weak acids and bases, and we need to understand those equilibria. And one way we do this is we have a new constant. Now please do not confuse this K. This is equilibrium constant Kc or Kp. And what would happen here is we would take, it's sort of a ratio. This is a way we kind of talk about the position of the equilibrium. Does it favor the reactants or does it favor the products? Because although I did with my diagram here showed that the concentrations of these were kind of similar, right? This went down to 0.4 molar. This went up to 0.6 molar. The rate of change of this was half, so it went down 0.3 molar to 0.7 molar. And these are very comparable, but quite often they're not. And they might be really, really big concentrations of the products or big concentrations of the reactants and small concentrations elsewhere. And so this tells us the position of the equilibrium. So what we do is if we're using concentration, which most of the time we will be, we take the concentration of the products divided by the concentration of the reactants and raise it to the power of their coefficients. So something like this example, we would take our reaction products, we call this Kc by the way, would be concentration, put that there so you can kind of see it, of NO2 squared divided by the concentration of NO squared divided by the concentration of O2 to the 1 power. And that's what we would do for that particular reaction because it has a couple coefficients of 2 in there. And actually, in this particular case from my graph, if I cared to, I could plug in my numbers. So in my little, and then what we do is, by the way, it's kind of cool. We leave the units off. So this would be have units of inverse molarity, but we just say, hey, there could be infinite numbers of kinds of concentrations here. So that, by the way, this was in my little diagram. NO went down to 0.4 molar. So we, if we have a little graph like this, we could 0.4 squared divided by the O2 was 0.7. So we could plug all those concentrations. Now that's just to the 1 power. And we'd get a number. And that number would tell you something. So we'd say 0.6 and we'd square that. We'd divide by 0.4 2 times. And then we'd divide by 0.7. And I'd get a number of 3.2. What's that tell the reader? That tells the reader that, well, this is something that leans a little bit towards the products than the reactants. And so, by the way, we could do this with pressures. This is called Kp if it's pressures. This is with concentration. And so what happens is a couple different sort of scenarios. If K equals large, that tells us that the equilibrium favors the products. What if K is small? Kc or Kp, it tells you the opposite. That's reactant favored. So the size of K is determined by really the stability of products or reactants. Something that has a small K, you'd say, well, nature tends to favor the reactants more than the products. And if something had a big old K, we'd say, well, nature wants to form more products than reactants. So the K value tells you a lot just by looking at it. For example, the K of acetic acid, which is a very mild acid, and its ionization, the K of its ionization is 1.8 times 10 to the minus 5, which is really, really small, but that's why it's such a mild acid. So these K values tell you a lot, and we're going to use them right now. Actually, I kind of lied. We're not going to use a K yet. We're going to use a K in another example, but here we're going to calculate a K. So, folks, these are very much what you'd call story problems, and the old equilibrium constant problems really lend themselves to that. But that's okay. You have the same strategy for solving these, and it involves a R.I.C.E table. I used to call them ICE tables, but I like R.I.C.E and I like R.I.C.E table better because it includes the steps in the word R.I.C.E, how you set these up. So here's a story problem, blah, blah, blah. There's our same exact scenario I drew a graph of. Here's the reaction. That's the R in R.I.C.E. If 1 mole per liter of NO and O2 are placed in a vessel and allowed to react, the concentration of NO diminishes to 0.4. Calculate Kc. So what does a R.I.C.E table entail? R is the reaction. All right, I wrote that down. So you just go down, copy the reaction that's given to you. You'd have to be given a reaction or something's really weird. So I did that. And then what did they give us? They said if 1.0 molar of NO and O2 are placed in a vessel and allowed to react, that means that this is 1.0 molar. I'm going to leave the M off just to make it easier to see. And this would be 1.0. They didn't mention any of this, so that means that that's 0. And I stands for initial. Reaction, initial. C stands for change, and then equilibrium. So what they say, the concentration of NO diminishes to 0.4. I should have put in my little example. At equilibrium. It'll say that. I just missed those words. So at equilibrium, the concentration of NO diminishes to 0.4. That's the E line. And now we can finish and solve the whole problem. So R.I.C.E. Now, the thing is, I don't have to be a huge super sleuth to tell that that change was from 1 to 0.4 was negative 0.6. That tells you the change of the other components too. Watch out though, coefficients are important. Every 2 of those NOs that are disappear, take with it 1 O2 and produce 1 NO2. So the change here is actually less because it's minus 0.3. You see what I did there? That change line should reflect the coefficients. And now the change here, every 2 of those that is destroyed creates 2 of those. So that's a change in plus. Now, by the way, I'll see students put negative for everything, but you can't go negative from 0. That would be negative moles per liter. And so then what happens is we're going to calculate Kc, but 1 minus 0.3 is 0.7. 0 plus 0.6 is 0.6. And you plug these into the K, and once you have the reaction, you can write the K. K is going to be concentration of NO2 squared. I know this, writing it over again, we wrote it in the previous my previous little spiel. And you plug numbers in there, 0.6 squared divided by 0.4 squared divided by 0.7. And I know I just did it, but 0.6 squared divided by 0.4 divided by 0.4. And I'm just paranoid. That's my problem. So divided by 0.4 divided by 0.4 divided by 0.7 is 3.2. So that's how we would calculate the K value from the equilibrium and initial concentrations. But what if we don't know that? What if we, and actually what's more useful is to use a K to predict what's going to happen at equilibrium. So that's what we're going to do. We're going to do a little switcheroo next where we use a K to calculate an equilibrium concentration. All right, here we go again. This time we're going to come at it from a different angle. We're going to be given the reaction and the K. Kc is 55 degrees. C at 25 degrees. They always quote a temperature, but you never end up using it because we haven't done anything with temperature yet, have we? But see, just ignore that part as if it's trivia. If 1 mole per liter of H2 and I2, these two, are placed in a vessel, what are the concentrations of all components at equilibrium? So if you need to get started, need to get lubricated, one thing I know I can do right off the bat if I'm given the equation is I can write Kc, that would be Hi squared divided by H2 to the first power and I2 to the first power. They're telling us that that's 55 is the value of K. Once again, R.I.C.E table. So I'm going to go ahead and write the reaction and then the initial concentration. First, just, get started by writing the reaction. All right, and then we got makes 2Hi. You might even want to throw some of this stuff in there. Throw in some X's. Every X of those that disappear create 2X of those. So they told us in the text of the problem, if 1 mole per liter, that would be I. H2 and I2. So okay, nothing else are placed in a vessel. What are the concentration of all components at equilibrium? We need to find out what's on the E line. All right, you'll see that this one sets up a little bit different. 1.0, 1.0, 0, and that's it. So what do we do? Well, I know this. When we don't know what something is, we're going to call it X. Ooh, it sounds like a solve for X problem, huh? So minus X plus 2X. So at equilibrium, the concentration of H2 and I2 will be 1.0 minus X, 1.0 minus X, and 2X. 0 plus 2X is, now we've got ourselves an algebra problem. Because now what I'm going to do is I'm going to plug all that in to Kc. So Kc equals 55.0. That is equal to Hi squared would be 2X squared divided by 1.0 minus X divided by 1.0 minus X again. You see that? All I did was take everything from the E line and bring it down. That's all equal. Now here's the thing. This might have you panicking, but I'll tell you what. You don't get any style points for making this more complicated. You could say, I'm going to FOIL out the bottom here, and that's in the denominator. The numerator, I almost said. That's in the denominator, and you're going to make the denominator more complicated? I'm going to just kind of recognize after you do these things, that's the same as saying 2X squared divided by 1.0 minus X squared. So we got lucky there that those initial concentrations were the same. That's all equal to 55. So let's take a square root of both sides. If I take a square root of 55, I get 7.4. Let's just call it 7.4. If I take a square root of both sides, then the left side would be 2X divided by 1.0 minus X. That simplified a great deal, and I didn't make it extremely complicated because it didn't need to be. One thing that's happening is I'm running out of paper though, but I got plenty more where that came from. Focus, focus. Okay, so now what we're going to do is we are going to focus, and we are going to go ahead and multiply both sides by 1.0 minus X. 2X equals 7.4 times 1.0 minus X. Fair enough. Distribute the 7.4 through, so 7.4 minus 7.4X. Now here's the thing, I can tell you that I've seen people goof this up, and I'll tell you how they'll goof it up instead. They'll, let's add 7.4X to each side. There's ways you can check yourself before you wreck yourself. So the left will be 9.4x equals 7.4. And I'll see people get this backwards, and they'll divide 9.4 by 7.4 instead of 7.4 by 9.4. And then you'll know that it's jacked up because you can't have x be bigger than 1. That would give you a negative concentration. There's no such thing as negative moles per liter. So now 7.4 divided by 9.4 equals 0.787. Now we have to remember what 0.787 means. It feels like in math class we're done. We're not done. We need to use the x to calculate each concentration. So at equilibrium, the concentration of H2 is 1.0 minus 0.787. And so is I2, 1.0 minus 0.787. And HI is 2 times 0.787. So let's keep in mind that H2, that's what it's asking for, is the concentrations at equilibrium. And I2 equals 1.0 minus 0.787. 1.0 minus 0.787. And let's find out what that is. 0.212. There's 2/3 of my problem. What is HI? Back when we go back and look at our R.I.C.E table, HI is 2x at equilibrium, so it's 2 times 0.787. Now, I got a beautiful way for you to check yourself after we're done. 1.574 molar. That is our answer. And I'm going to now not just be happy that I arrived there. I am going to take a split second to plug it all back in to Kc. Kc was concentration of HI squared divided by H2 divided by I2. So let's do that. 1.574 squared divided by 0.212 divided by 0.212. And I better get something close to what K was. So how long is this going to take me here? Minute tops, divided by 0.212 divided by 0.212. And I get 55.1. So chances are I got the right answer because I plugged it back into K, got the same number back. And I've done this before where I've forgotten to square something and I'm like, oh, why is it not 55? I usually forget something, but you should be able to prove to yourself that you got the right answer by plugging it back in. And this is what's going to happen, folks. We're going to go and we're going to look up a K. There's tables full of Ks for all sorts of different reactions and calculate what is something at equilibrium, like weak acids and weak bases. That's coming up soon. That's the real utility of this stuff. I'll see you next time where we throw in some more weird examples of using Ks to calculate things at equilibrium. Until then, take care and salutations.